This is Dr. Holt. This is AP Physics C. This lesson and this video is on understanding power. Power is the rate at which work is done. So we can say that power is the change in work over the change in time, or dW over dt. However, we know that the change in work is nothing more than force times delta x. So we can rewrite power as force times delta x divided by delta t. We're just substituting in place of delta W, we're putting force times delta x. But if you note, let me get a regular pen, that dx over dt is nothing more than velocity, so we can basically say that power is equal to force times velocity. Now power is always going to be measured in watts, and 1 watt is equal to 1 joule per second. You often see the term horsepower used for power. Now 1 horsepower is equal to 746 watts. So sometimes you'll have to make conversions. An example here, if I have a man who's trying to push up a refrigerator up a ramp, and let's call this distance to be 1 meter. Then what we could say would be that the work that this man is going to do would be the mass of the refrigerator times gravity times 1, and that would be the work. Now the man down here would do the same thing if this distance was 1 meter. So the work this man would do would be mass times gravity times 1. But you notice the ramp here is shorter than the ramp here. So the time required for, let's say, this man to push it up the ramp, since it's a shorter distance, would be 2 seconds. So the power here would be equal to delta change in work over change in time. And that would just be equal to mg times 1 divided by 3. I'm sorry, divided by 2, being the time, 2 seconds. Now if we look at the example down below, the ramp is longer. So let's say the time is equal to 3 seconds here. Then the power required would be the work, which would be mg. And again, I'm leaving out the 1 because mg times 1 is just mg. We divide it by the time. Make an S better back here, sorry. Looks like 36, I'm sorry. 3 seconds. And that would be 3 seconds. Boy, if I could write today, huh? 3 seconds. So here, the power would be mg over 3. So it would require more power here to get the refrigerator up the shorter ramp than would the man to take it on the longer ramp, because he has more time to do that. A good example here, we have an elevator car. It has a mass of 1,600 kilograms. It's carrying passengers having a combined mass of 200 kilograms. A constant frictional force of 4,000 newtons retards its motion upwards as shown above. What power is required to deliver? What power delivered by the motor is required to lift the elevator car a constant speed of 3 meters a second? Alright, so we'll draw ourselves a free body diagram here. Let me go back to the black color. Alright, so I will find out what the total mass going down would be. Let's go back to the picture. So our total mass would be 1,600 kilograms. We have 200 kilograms of passengers, so that total mass would be 1,800. Multiply that by 9.8. Alright, now we have a retarding force. I'm going to go back so you can see this. Of 4,000 newtons, a constant frictional force of 4,000 newton retards. So we'll make that 4,000 newtons. Now we have force has to go up. Now if this is going to move at a constant speed, then the force here has got to be the sum of this. Basically, because we're doing this, the summation of forces in the y direction must equal to mass times acceleration in the y direction. But we know the acceleration is 0 because I got constant velocity. So that means the forces have to add together to be 0. So all we have to do now is sum the forces here. So if I sum the forces in the y direction and set them equal to 0, I will get F minus 4,000. Go back a little mark. Oops, hang on, let me just erase that then. Minus 1,800 times 9.8 is equal to 0. We will get F equal to 21,640 newtons. Again, we can go back and we said that power is equal to force times velocity. Again, I'll go back and show you where that comes from. That comes from right here. Power is equal to force times velocity. So I take 21,640 newtons. I multiply that by 3 meters per second. And that will give me 64,920 watts of power. Okay. Now if we want to find out how much horsepower is required, all we would have to go back to, I'll go all the way back so you can see where this is coming from. We know that 1 horsepower is equal to 746 watts. So if I take this number here, 64,920 watts, I divide that by the 746 watts required for 1 horsepower, and I will find out I will get 87 horsepower. Alright, so there's your 2 power requirements. Alright, let's look at another problem. This one, I have a car, has a mass m, is accelerating up a hill as shown above. An automotive engineer measures the magnitude of the total resistive force to be 218 plus 0.70 V squared, where V is in meters per second. Determine the power the engine must deliver to the wheels as a function of speed. Alright, scroll down here, draw a free body diagram of this. So I'll break this into components here. Now this would be the force normal. Now we know that this value would be mg times the cosine of theta. We would know this value here would be the mg times the sine of theta. And now this would be the resistive force. So let me go back and get that, which would be 218 plus 0.70 V squared. Okay, and we want to see what determine the power, and let's see if they had acceleration. Okay, so we need a force. So this is the force that the engine's causing on the wheels to get an acceleration. So we go back and we make that our force. Now we just go back to Newton's law, the summation of forces, and we'll call this our x-axis. Whereas the x must equal to mass times acceleration in the x direction. So if we do that, we will get force minus 218 minus 0.70 v squared minus mg sine theta must equal to mass of the car times acceleration in the x direction. Okay, so what I want to do here is I want to solve for F. So we could say that F is going to equal to the mass of the car times acceleration in the x direction plus 218 plus 0.70 v squared plus mg sine theta. Now we know again that force times velocity is equal to power. So all I have to do to find out what the power would be is I'm going to multiply everything by v, and then on the left side I will get power. And that will give me mass of the car times acceleration times the velocity. We'll make it a velocity vector because it's going up, plus 218 times v going up plus 0.70 v cubed. And again, I'll show that as a vector only because it is a velocity, it's going up, plus m gravity times v times the sine of theta. And that's how we'd get our power equation. So again, here's an example of how to do this specific type of problem. In this lecture I've gone over basic terms of how to find power. Again, all it is the change in work over change in time, or force times velocity. And I worked a few problems to demonstrate how to use the proper techniques.